Okay.
Just
Yeah.
let me know.
Yeah, it should be streaming now. You can start whenever you want.
Okay. So hi, I'm gonna be presenting this preprint called "The Dead Salmons of AI Interpretability," and it's a preprint we submitted just last week, I think, or 2 weeks ago. And I
Maybe
should mention.
put your mouth a bit away from the mic since
Okay.
you're
Is it
being into it.
saturating a bit?
Okay.
Hang on. Okay, let me know now if this is a bit better.
That's a little bit better, yeah.
Yeah, I don't have an excellent mic, but okay. Just let me know if needed. And yeah, this is a very much a position paper, so not a classic experimental paper, even though there are a few experiments. And so basically, there are 4 parts in this presentation. The first one is kind of a related work showing what we call the statistical fragility of AI interpretability, and then figuring out why that happens and what we can do about it. So the name of the paper comes from a pretty famous study in neuroscience that came out in 2009. And basically, neuroscience researchers put a dead salmon, so a dead fish, in an MRI machine. And so, of course, it was a dead fish, and they knew that it was dead. And they showed the salmon a series of pictures showing humans in situations like in a picnic or dancing, things like that. And they asked, again, the dead fish to determine what emotion the person in the photo must have been experiencing. And what they did is that they applied the standard analysis science to measure brain activity on the salmon, and they found that there were several regions of the brain that were statistically significant with the actual task the salmon was asked to do, even with a very high, very low p-value. And obviously, it's not like a study about magic salmon or anything, but what was going on is that obviously, even though the measurement was correct, the inference that they did was flawed. And essentially they were just random noise because again it was a dead fish with no actual brain activity. And here the goal of the study was to show that if you don't correct for multiple comparisons, then you can end up with a nonsensical result. And the reason why this study was important is that in neurosciences it was part of what we call a statistical revolution, where people started identifying other statistical issues such as that one. So typically issues where methods would find false positives, issues of overfitting, spurious correlation, so correlation between different phenomena that were not actually based on causation. And what happens is that similar issues, for example, in psychology, econometrics, social sciences, during the replication crisis, there were issues where also people were finding that there were things that were not done properly in terms of statistics and that was leading to wrong results. And so essentially what we call dead salmon issues, it's things like reading patterns where there's actually only random, even though we seem to produce what looks like a plausible interpretation. And in all of those fields, the way it is over time by building stronger statistical frameworks, correcting comparisons. The entire field of causal inference is more or less born from the statistical revolution. So that's how it was done. And so what we do with this work is that, first of all, we try to find similar dead salmon and more generally statistical fragility in the field of XAI. Then we try to find what is the cause, where are those issues happening, and then one possible solution, which is tentative for now. So first, let's do the related work part. And here's a minimal example, actually, experiment. Simply put, we took BERT and randomized all of its weights, pretty much just keeping the embeddings and then randomizing everything else. And what we did is that we fed BERT with 300 IMDb sentences and measured the activation, the average tokens. And we tried to see if we could get, this was a sentiment analysis dataset, if we could get an actual positive correlation between the activations of this now randomized network and the actual label of the data. And what you can see in the top half of the picture is that we were finding a lot of similar correlations, even with very low p-values. In the second step, we did something similar as well, where this time we still kept randomized BERT, and this time we trained the probe on different layers of the model to see again if we could predict the label from the activations. And what we can see is that the probe significantly all of the time outperformed random guessing. We're getting accuracy of about 0.8 plus or minus 0.15. So we have a double type of analysis. On one hand, we have PCA on the top. This is PCA, and the second one is probing. And so we have this random network, but we're still able to infer things that looks like the model is actually doing something, even though it's again a completely random network. And this mostly comes from the fact that there is already data in token embeddings, and even though the model does nothing after, that information is pretty much preserved, and that's why we can find such correlations. So this kind of dead salmon artifacts, they were found even in feature attribution methods, where people showed that even if you randomize pretty much all of vision models layers, you can still find that saliency map produce what look like plausible explanations. So you can see in this bird image for different methods. From left to right, it's randomizing more and more layer, and at the end, the is completely randomized pretty much, and you can see that saliency maps still produce things that pretty much look like the original image. So this was kind of the first work showing this kind of issue. Other similar, more generally statistical issues were that, for example, explanations can be manipulated. So here on the top, you can see that we can add adversarial perturbations to an image, and then the either saliency map or depending on your explanation method, you can produce pretty much whatever you want. Interpretation of neural networks is fragile. And then at the bottom, impossibility theorems for feature attribution. This was a theoretical work which showed that if you take any feature attribution method that's complete and linear, so for example, integrated gradients, SHAP, and so on, you can mathematically prove that they fail in some situation and can simply not be better than random guessing. And this was tested on a large class of models. Then we have probing, which is still widely used. We fairly old studies again as well, that probing can recover information even if the contextualized embeddings are randomized. We know that there are a lot of examples where probes don't really generalize very well. And also the issue is more fundamental. Probing will pretty much check if some concept is present in the activation of a model, but it doesn't necessarily mean that it's actually using activations to do anything. Now, more recently, we have SAEs, and we also know a number of issues with SAEs that they can be used to interpret even formers randomly initially. They also have generalization issues that have been shown. The 2 papers in the middle pretty much show that. And the last paper at the bottom shows that sparse autoencoders are sensitive to adversarial input perturbations. So all of us, again, it's not necessarily exactly that sound points to a general lack of robustness in those methods. We also have concept-based explanations. So one paper from 2021 shows there's the presence of what we call interpretability illusions. And what those are is that essentially we find spurious correlations between activations of some neurons and concepts. So there seem to be correlation, but they are not actually causal. Spurious correlation. Then we also know that concept activation scores can produce inconsistent explanation, and in general, concept-based methods they tend to have poor generalization, and they are highly sensitive to the data set that produce the explanation. Then a bit more recently, we've had a lot of causal approaches. Typically, for example, causal mediation analysis, which is patching. So again, when we perform interventions on intermediate work to try and measure the effect of a component. And here again, studies have shown that these are experimental design. And there's also what has been termed the Hydra effect, which shows that even if you find a component that has an important score, so mediation score, meaning that the component seems to be important in the behavior that you're explaining. If you remove that neuron or that component, the model still works because there's superpositions of states and different redundant pathways in the computational graph that makes it so that the neural network is still able to perform the task. Then in actual mechanistic interpretability, also have similar issues that have been showed more recently. So interpretability, again, they seem to appear even in methods such as subspace activation patching. There are some studies that have shown multiple times that circuits don't generalize very well. I also submitted a preprint recently that showed that circuits that we observe with circuit discovery methods, they are sensitive to very small minor choice. If you perturbate your data set a little bit, you can have very different circuits. Another study that I presented in this reading group a while ago shows that in a single network, you can find multiple circuits that are completely different, even if the network is randomized. And then another paper, which I think was also in this reading a few weeks ago, shows that even methods like causal abstraction can produce explanations for random networks. So all of these, again, point to some issues. Oh, and there's one other thing that I didn't mention here, which is explanations in natural language, reasoning of thought, or things like that for the model. There have also been studies that shows that the natural language explanations are not necessarily faithful to the actual computation going on inside the model. So if you had to ask the model, how did it come up with the result, it will produce an explanation that it actually computed the answer. So what are those issues coming from? Well, essentially, there are two big issues that we call underspecification and overdetermination. Underspecification is the fact that sometimes if you just look at input-output behaviors and you want to explain that, well, simply put, you can just overfit, and there are an infinite number of different explanations that can fit the data equally well. So that is underspecification, so input to output data is not enough to produce a single explanation. And overdetermination, a bit of the opposite, and overdetermination is the fact that you have multiple paths in your neural networks that are redundant. And each of these paths is independently sufficient, meaning that it works with the other, and that removing part of a network doesn't necessarily that it will fail on the task that you're evaluating out. And if you look at generally explanation methods, we have predictive methods and causal methods. Predictive methods, they tend to be of the first kind, so input to output behaviors, and therefore they are likely to have issues of underspecification. And if you look at causal methods, well, there's the second issue, so the problem of overdetermination. And more generally, there's a stronger concept, which is the concept of identifiability or non-identifiability. And in statistical inference, identifiability is the idea that if you have a model and you're trying to recover its parameters, can you do that uniquely from observations? So by just observing your model, can you recover the parameters in a way that you will get the actual parameters and that there's no multiple valid values? And why is identifiability not always happening? Well, as I said earlier, if you have poor generalization or overfitting, that means that your models are likely to produce different explanations depending on how it's overfitting, or you can have an explanation that generalizes badly in many ways, and that means that you don't know which explanation you should select, because again, they don't generalize, so it's easy to generate as many explanations as you want. If methods are sensitive to this choice, it also means you're going non-identifiability, because again, if you change slightly the parameters of your methods, you might end up with a different observation, so cover the unique true value. And there's also cases of false discovery in general. And the problem is that if you have a problem that is not identifiable, then that means that the bigger your hypothesis space is, then the larger the chance is that you're going to recover a false explanation, an explanation that is just spurious in general. And if we look a bit at some of the problems that we can find in the literature. So for example, for concept-based methods, concept activation vectors is quite a popular thing, but we can actually show that it's a non-identifiable problem, meaning that without additional not produce a unique explanation. More generally, this is an instance of causal representation learning and work that shows that it's underspecified. You can overfit in many different ways and produce explanation. For probing and SAEs, again, you are mostly input-output behavior or input and hidden state behavior. So this is a non-identifiable, again, because of this issue of underspecification. If you are only parts of a network, you can have an explanation that generalizes badly in plenty of different ways. And so that doesn't let you select a unique explanation. In the case of activation patching, we can actually show mathematically it is identifiable. So if you do patching and you fix your model and behavior, we find one exact value. But the problem is that people tend to overinterpret the results of causal mediation analysis. What this really tells you is that you can tell that one neuron or layer a certain score of importance, a certain effect score for a given behavior, but that doesn't mean that the behavior is located in place, which was the issue that we had with probing earlier. And that is, again, a case of overdetermination. You might remove and still have a behavior happening somewhere else. And circuit discovery, again, suffers as well. So for current methods, it's very much non-identifiable. And also identifiability in general is pretty hard to prove. So I'm only here, but there are many ways of explaining things for which we don't know are identifiable or not. This is very much an open problem. So now here I will present one of the proposed to all of these issues, which is called statistical causal inference. And here's a simple solution to the largest dead salmon issues, like the bird earlier. We try to run it on sentient what seemed like random explanations. So a simple solution is just to do hypothesis testing against a null hypothesis. So for example, when we explain a neural network, we produce one single explanation circuit or one single probe, etc. And one simple solution is to compare that explanation that we're producing against the same explanation, but produced on a randomized neural network with exactly the same architecture. So for example, if you are applying circuit discovery, I don't know, llama or whatever, just apply the same circuit discovery to a randomized model and then compare those two circuits together. And then mathematically, we have estimate the p-value using Monte Carlo, and that will score on how much your probe is extracting an actual explanation and not just reading random data, essentially. And so if we do that, we made 3, again, very small experiments. It's not really the main goal of the paper, but for the sentiment analysis, you can see on the left, this was the probe accuracies that we trained on the neural network. And you can see that the actual model is in blue. So when we train a bunch of different probes on the neural network, we get accuracy that tends to increase. And then if we train the same probes on, this time, the randomized neural network, we get those trajectories that are in gray. And so essentially, if you have a random beginning of the model, because it's simply encoded in the embeddings, but as you go through the random layer, result and accuracy. Whereas the actual trained model obviously is getting a better and better representation, and the probe increases. And what you can see is that on the right, we measure the effect size of the difference between those two groups. So again, the random neural networks and the actual one. And you can see that, so the orange bars here are when you probe versus random guessing. And you can see that here on the left, random guessing 0.5 for a two-label classification task, and that even the random network are outperforming guessing. And of course, the actual trained models probe is get extremely high and extremely. However, when we do the difference not with random guessing but with the randomly reinitialized model, we get much smaller effect score, and actually none of these are significant. So the probe is actually not performing significantly better than on a random network. So that is a way to correcting for this kind of issue. We have two similar experiments here. This one is pretty much the same thing, but instead of being used on sentiment analysis, it's simply on part of speech tagging prediction. And again, here you can see that if you just look at the probe on the train model, it performs very highly, way better than random chance, because there is, again, part of speech information encoded in the embeddings. So you get extremely high effect score again. But if you compare it to the same probe but trained on a randomized network, then you can see that there is a significant effect between layer 1 and 9, but the other layers between your trained probe on the actual model and on a randomized model. So this is, again, the kind of comparison we're looking for. And the last experiment here, we tried to reproduce the experiments of a paper that is called Language Models Represent Space and Time. And what the authors did in that paper is that they prompted a large language model place names such as New York City, Berlin, city names. And then they looked at the activations of the last layer, and they trained a probe on those activations to try to predict the real-world coordinate of the city, so the longitude and latitude on the actual world map. And they looked at the correlation, so the accuracy of the probe, so in terms of R-squared correlation between the actual location of and the one predicted from the activations. And again, as you can see, the probe was getting very high accuracy. And we did the same, but again, randomizing the neural network. We tend to get slightly lower accuracy, but still better than random chance. Again, due to the fact that most likely there is some spatial information about places. And here we can see that the result is that here the result is much always significant, but by comparing to a random network, instead of comparing to random guessing, we get a much smaller size. So it allows us to show things with a little bit more. And so the more general idea is that if you look at statistics in general, the process of statistical estimation is that you have some kind of hidden process, and you know that this process has true parameters theta that you cannot read directly. And what you do is that from that process, you visualize, you have observations, so samples of the process, things like that. And then you have an estimator that takes into input the finite observations and try to theta with a hat, so the estimate parameter. And we know that when we do that in statistics, then all kinds of properties that we might want in the estimator. So bias, which is simply put, does the estimator recover your correct parameter on average? Variance across different data sets, and consistency. So if you have observations tends to infinity, does your estimator converge to the true value of theta? And in this case, identifiability is not a property of the estimator, it's a property of a model. So what that means is that, simply put, identifiability means if you had a different process with a different value of theta, would you produce a different distribution of observations? And so the idea is to kind of use this kind of framework, in our case, for explanation, AI explanation. And so the first thing that we do is represent structural causal models. And structural causal models are essentially just graphs in which the nodes are variables, and the edges between nodes, they say how do you obtain a variable based on its parents. And this framework works very well. You can very easily to represent neural networks, because you need a causal graph, and the causal graph, in the case of a simple computation graph of a network. We have in a causal model what we call exogenous variable, external variable that act on the system. So in the case of a neural network, it would simply be the inputs. The inputs are not really a property of a network, it's just whatever puts in there. And you need to specify their distribution. Then we have what are called the endogenous variables and internal variables of a system. Things like hidden states, outputs, weight, things like that. And the last thing you need is what are called structural equations, which explain how do you go, how is obtained from the previous variable, the parent variable, and in the neural network, how to obtain the value of a neural network. Well, it's simply the propagation of the previous weights and values. So here would be things like attention, activation, functions, and so on. And then what we do is that we formalize causal queries. And a causal query is basically any question that you can answer if you know the true causal model. So if you have your neural network and have the graph, what kind of queries would you like to know? For example, what happens, what does the network produce in distribution if we force an activation to have a specific value? Or how much a certain attention contributes to a certain task like factual recall. And these are generally the kind of explanation that we're so we call these causal query again. And then the last thing we do is that we formalize surrogate models. And what we say is that an explanation is a simpler description of your model that can answer some kinds of causal queries about the underlying causal model. And so specifically, we have three components in what we call an explanation defined this way. There's a query space, meaning what are the queries that your explanation should answer? So what are the things you are trying to behavior? What kind of questions do you want to be able to answer? Then what we have is the surrogate class, which means which type of explanations am I, which type of explanations are admissible? Am I looking for circuits? Am I looking for a probe? Looking for causal graphs? And then we need some kind of error measure, meaning that given an explanation, how can we measure that that our explanation correctly answers the queries that we're trying to do? And so these are pretty much things that research. When you define an explanation, when you're trying to answer some question about you need to say which type of question you are willing to answer, which type of explanations are you accepting, and which error measure are you using. So these need to be precise by the researcher who is doing the explanatory work on the model. And then to evaluate explanation, basically what we want to measure is expected value of the distance between what your surrogate model produces and what the true answer to the query is. And what we say is that a task is identifiable if there is a unique way to minimize this. So essentially a unique surrogate model that minimizes the distance between the actual query answer and the one that your surrogate model is predicting. Of course, in practice, you cannot compute the actual value because if you're working, you can only use a finite amount of data. And even for, well, you can first of all answer only a finite questions, and even for each question, you can only do a finite number of sampling inputs and measuring, for example, activations. But that's fine because we can basically see this whole method and just theoretical estimator. Since we have a finite data set, we are an explanation that is an estimate. So here's a little example because I know. So as you can see again, the causal model in terms of work, we're going to have some kind of input distribution that we are assuming. Then the neural network, which is your causal model, so your computation graphs. And then for circuit finding, we need to specify what are the three things that we need for explanation. The first one is the type of queries that we want to answer. So this depends why we're doing circuit finding. I don't know, indirect object identification, then our queries are going to be these type of questions. Then what are type of space, what type of are we allowing, finding, accepting only circuits, which are subgraphs of your neural network. And then what is the error measure? Well, here for a given query and explanation, your error measure would basically be the divergence between the distribution that your model produces and the distribution that your model produces if so this is just one such example. But what's really interesting is that you can kind of theoretical framework to reframe all kinds of different results. So for example, if you just want to do performance benchmarking on your model, that is technically a type of explanation. It's just that your surrogate model, let's have a model on a task, then basically what you're looking for is a model color that summarizes your prediction, for example, accuracy. And here, what would be your causal query? Well, your causal query is assuming a certain distribution of inputs, what should be the distribution of the output actual theoretical accuracy. And then you are going to measure that accuracy with a finite number of samples. And so you can measure the error, which was simply going to be the difference between the expected value, your estimated value versus the true one. You can also reframe all kinds of things like this, probing, concept-based methods, and so on. Circuit discovery, causal tracing, causal abstraction. And eventually, the idea is really just for each thing you want to do is you need to specify what type of questions do I want to answer, how do I formalize these causal models, then what types of answers do I use to judge if an explanation is good. So what are the benefits of doing this whole theoretical, I guess, grounding? So the nice thing is that essentially it turns the task of explaining into an objective. And when it's an objective inference problem, we know that we can kind of mathematical tools to treat that and check for the fact that it's actually robust and so on. However, there's one thing which is it's both an additional constraint, but it's also nice. If we do the statistical framing, it's that we need to report uncertainty. So for example, for a circuit, you cannot just have a method that produces one circuit. Here, since you're working with probabilistic inputs, you need to give some kind of confidence set or posterior distribution. So you need to qualify the uncertainty that your method will produce. And in general, we know that if tasks are not identifiable, tend to produce results with high uncertainty. If the task is identifiable, we should get low uncertainty. And the other thing that is nice is that if we frame interpretability is I wrote probability, a property of the method and not the model, meaning that for a given model, you can change your allowed explanation, queries that you're trying to answer, and tweak these to try to improve the idea of what you are doing. And then in terms of future, done with it. In causal inference, what they try to do, tasks are identifiable or not, and here it's the same thing. So given a collection of queries, given allowed explanation divergence measurement, can we tell if that triple is identifiable? And that would help us figure out, again, which tasks are easier or harder in the grand scheme of explainability. What's also nice is when everything that Bayesian approaches. So for example, saying in advance, you can specify a prior over type of explanations that you're looking for, and then applying classical posterior update rules to try to refine your explanation over time. And finally, this is also nice because it essentially opens the door to meta-analysis and cumulative science. So for example, you can simply aggregate evidence from multiple studies and apply those findings together to get a stronger, like a smaller confidence interval or a stronger bound of whatever effect you are trying to measure. So thank you very much. If you have any questions or if you want me to go over things again, please feel free.
Okay, thanks for the talk. I was only able to make some of it, but I'm glad I was able to make some of it. I have questions about the last two slides.
Yes.
The one that comes to mind most right now would probably be this future work here. So, can you explain a bit? I think I'm a bit cautious. I definitely think mechanistic interpretability is a field that is like in strong need of becoming a cumulative science, and it's far from it right now. I think like it's not clear exactly how this Bayesian approach that you kind of loosely sketched out will actually lead to that, because I think there's too many distinct things that the cumulative effects of different studies work on. They're like too many. Like there's like combinatorial explosion is a bit too big, such that I don't think things will align such that you can simulate them in this way.
Yeah, no, I would say those are two different. The cumulative science part is just gathering evidence in general for a specific behavior over different studies, but the Bayesian approach would really just be for a single task that you're trying to explain and just accumulating evidence for that task on a single model, probably within the context of a single study. And yeah, I agree that for the part, I mean, it is a bit speculative because again, you have so many models and data sets and so on that it's like I could see the amount of data actually being available being very sparse and not necessarily lending itself to this kind of analysis. But at least it opens the door to it, is what I would say.
Yeah, cool. Let's go one slide back. Sorry, I went on a bike ride. I had to go bike between two places, so I missed like the 10 minutes before this. But I just want to spend a bit more time on this sentence at the bottom, which is identifiability is a probability of the method, not the model.
Yes.
Yeah, can you just like say a bit more words, because I missed the time before that.
Yeah, so essentially, again, if you just look at statistical estimation, identifiability is a property of your model. It's just, simply put, given an infinite number of observations of your model, can you always, well, no, it's not even that. It's just if you have different values of your parameters, does that produce a different distribution over the observations that you're measuring? And so essentially, if your process is not identifiable, I mean, there's kind of nothing you can do about it. And the idea, well, part of our framing is that the identifiability is not really, I mean, we have a slightly different definition of identifiability, and it's just saying that if you have a queries you're trying to answer, you have a class of explanations that you accept, and you have a discrepancy measure, then the identifiability is a property of this triplet, and say using this triple, is there a unique explanation that makes your divergent a set of queries based on the model that you have. And so if you have something that is non-identifiable, you can simply make it more identifiable by decreasing the size of the allowed explanations or just trying to answer less queries. So this is something you can influence on because it's a property of the model, but really of the explanation method that you are proposing. Does that make sense?
Yeah, I think so. This is a big question, but obviously my question is motivated by my own research. What do you think about the plausibility or tractability of kind of jointly tuning the model and the method conjunctly to allow greater identifiability?
So training the model at the same time as the method. Yeah, I mean, yeah, I don't see why that wouldn't work, because, I mean, there are a number of approaches where this is what a lot of people do, is just try to train the model to be more explainable. That's one way to do it. But if you can also train, so refine your the type of explanation that you're producing, yeah, that should be another way of doing it. I don't see any immediate issues with that.
Yeah, I have more questions, but if anyone else wants to ask, I want to let them ask as well first.
I had just one question. So you listed almost every method that's used in Mech Interp, except I guess for tiering vectors. And I'm wondering what do you think, how this could be basically applied to also make steering vectors more empirical. Like, in a sense, we sort of already do it by having random vectors and seeing if that does something as well. But other than that, maybe we could improve on it as well. Like, what's your take on that?
So I will admit that I'm very unfamiliar with steering vectors in general. It's kind of a black spot I have in in my later work. But well, again, I guess the simple thing to do would be like to begin with just the comparison, like the hypothesis testing. Again, like you compare with a random vector and you see if you get something that's really different. I think that would be a pretty good start to that. And can you reframe the whole idea of steering vectors into this? Yeah, I mean the framework should be able to accommodate that, and we can try to quantify exactly what kind of questions are you answering, and then here your explanation class would be like a set of vectors essentially, and the hard part may be the measuring part. But the basic thing would be at least doing the hypothesis test against a baseline and seeing if you get. I don't know if there are already studies that do this kind of, but that would be the first thing that would come to mind.
Yeah, that was my question. So basically, something like null hypothesis exists for steering vectors, which is that
Okay.
you try to see if adding a random direction vector would also make a similar change, which is like a one sanity check that exists. But yeah, based on your presentation here, more could be done in that direction, I guess. Yeah.
Yeah, most likely. I mean, more can always be done. But the problem is that again, it makes it harder for the. You don't just blindly apply a method, but now you need to say exactly what do I want to answer and how to answer it. So it shifts the burden in that way. But I think that's really the way to go. Rigorous mechanistic interpretability in general.
Okay, I'm back on my laptop now. Does anyone else have any questions?
I had some as well. I guess this is more specific. Like, just wondering if for instance, if I get it correctly, sometimes you can train sparse autoencoders on transformers or on language models, and if you increase the dimensionality of the sparse autoencoder, you can possibly get like more granular features, basically. So that, in a way, is a form of non-identifiability, right?
Yeah. I mean, again, the thing is that you're just trying to predict a series of output from just one activation layer or whatever. If you just you can have a whole way to just make something that doesn't generalize on other types of functions. You can find as many potential working sparse autoencoders as you can imagine, all produce slightly different results. So yeah, what you're saying is changing the dimension of the hidden state, you end up with different concepts and things, and yeah, that's one thing that tends to prove that there's probably not identifiability.
Yeah, and also all sorts of like configurations like that can produce different feature splitting, for instance, different reconstruction loss problems, and so on. So that seems to be very, very brittle in terms of this non-identifiability. That's good point. Yeah. So we can mistake ourselves. Oh, this is the model. What it's actually doing in the sparse autoencoder in the attribution graph. But in reality, this is just one possible trained sparse autoencoder.
Yeah, pretty much. But that's also normal. Like you need to understand AI is recent and mechanistic and like 5-6 years old. So if we compare to other methods like natural sciences, but for 50, 100, 200 years, I think it's normal that we're doing this kind of sort of baby step. But I think part of growing up, part of mechanistic interpretability is going to understand this kind of issues and trying to solve them.
Yeah. Also, okay, maybe more general question there, but thanks for the answer there. That's true. And is like I feel, at least as far as I understand it, like in science, like to truly identify a causal relationship, you have to do some kind of intervention, and it has to be done correctly. So I wonder if you have like some good rule book that like to do it correctly, basically, to not delude ourselves, as Neil Nanda would say.
Well, that is one of the things that I did mention. Radiation analysis. I don't remember where that was, but that is yeah, that is a causal method, right? You're actual patching, so you're intervening and changing that if you move your component or change disactivation with a zero or a bean or a noisy baseline, whether you have a difference. So I mean, there's a lot of perspective, but I think we're currently already doing some of the nice things. The hard part again is not just because you have a causal effect in a neuron. Does that mean, like, yeah, you can prove mathematically again the effect, this neuron has an effect, but again, that doesn't mean, oh, that's where my behavior is, because you can remove that network, that neuron, and still have the behavior happening in other. So it can be used to quantify things well, but I think the hard part is jumping to the interpretation, and that I don't know if causality in general has any great answers to that. I work a lot with causal abstraction, so I think a nice idea in general is to give explanations as causal abstractions, and then you can kind of try to verify the study by Sutter and Julian Minder has shown, like it also has other type of issues. So yeah, I don't really know, but in general, yeah, if you just go beyond.
You're cutting off a bit. I think
sorry.
mic sensitivity is too low, basically.
Oh,
Right
sorry.
Okay.
Yeah, but essentially, yeah, if you want to go beyond correlations, you need to perform some kind of interventions. That's otherwise you're not even at level. I mean, you're at level 0 of causality. It's not.
Yes.
Okay.
But the Hyder effect is a thing, for example.
Yes. Yeah, it is very much.
Like what if I can give an example there, like what comes to mind is that people thought that like I'm not sure. Okay, well, the example that is that people thought that smoking causes that alcohol causes lung cancer, but actually the correlation was there because people who smoke also tended. I mean, people who took alcohol also tended to smoke,
Yeah.
so that's why the correlation basically. But like for instance, if in that person you would ablate the lung, then or okay. That's not a good idea. Ablations on humans are terrible, basically. You cannot really do that.
Yeah, I mean,
Trying to think of other examples where you can like see like ablation actually doesn't give you causal answer.
well, here
Then you
the
see a
intervention
correlation.
would
That's
be
why you
more
do it.
like
Yeah. That's why you
make
do
the
testing on
person.
animals.
Yeah, or that. But I guess in that case, yeah, if you want to show, if you have a person who's smoking and drinking, and you see that they have cancer, well, you cannot really do it on one person. You entire population. But here the intervention would be make a part of a group stop smoking or stop drinking, and then
Alright.
see if okay, well, you need a control group who doesn't have cancer, because stopping smoking is not going to make your cancer disappear, but you get the idea.
Yeah. Okay, that works. Yeah. Ablate the other causal variable.
Yeah.
But the issue is with the alcohol thing, they didn't think about the other causal variable. So sometimes in Mech Interp we wouldn't think, oh, actually the causal variable is somewhere else, and we wouldn't look for it and just.
But that's why, I mean, that's why, like, especially these kind of questions in econometry and medical science, if you want to, I mean, the field had to mature to be able to see, is something really a causal factor for a disease or a phenomenon?
Yeah.
Like that's how the entire field of causal inference was born, really.
Thanks. Okay, makes sense.
I have a question. Just curious, like, when did you work on this project? Over what time period? And who, like who helped you the most, I guess?
So this was mostly done with my advisor Maxime Peyrard, so the other Maxime here at the end, and we've been working on this for essentially my previous works were kind of showing those dead Salmons issues. So the paper that one of them was showing non-identifiability of circuit discovery, and then recently I had another try to show the variant circuit methods in general. I was like, oh, so interesting. We have identity issue be interesting to try and reframe all of that as a statistical problem, because we have the same type of issues we encounter in statistics. So really working on this paper, it wasn't very probably like a month or two, but there was a lot of earlier work or like preparing work that was done over since the beginning of my PhD, pretty much.
Cool. Is this a final installment, or is there like more like in the series?
Well, I have another big work coming up, which is, but it's more on causal abstraction, statistical part. However, I think it would be interesting to try and do some Bayesian causal stuff. So this might be a problem that something I would be interested in working on. Just see if we can do like, I don't know, Bayesian circuit discovery, Bayesian probing, whatever you want. So this might be a very serious on the statistical part.
Cool. Rectifies. Victor, do you have any questions?
Yeah, not really. I do want to mention that there is some mic artifacts on that, but I'll probably be able to fix them on the recording.
Yeah, I'm very sorry. I'm with my work headset, which is extremely poor.
Yeah, don't worry.
think
I think some of it I might fix it for YouTube later. But yeah.
Okay, thank you.
I think just the mic sensitivity, like in the Discord setting, you could lower it so that it catches up your voice more often, even if you're speaking slightly less loud, slightly quieter.
Yeah.
Yeah.
At the moment.
There's also like the small noises but I think the small noises like for the when you talk, that's probably fixable. But yeah.
By the way, do you think I think something that could be useful for Mech Interp people, if you wanna jump from this topic, Victor, is if you could like take this and make like some kind of cheat sheet or something, like for Mech Interp researchers or something, like here's do this null hypothesis, or think about like the non-identifiability issue, etc. Like, I think that would be like useful for yeah, the whole Mech Interp field, I think, needs more rigorous statistics, and well, generally the whole machine learning field needs more statistics. So
yeah,
I think yeah.
Yeah, that's true. That's something we can look into. Propagate the good word.
Yeah, but it's funny in a way, like how how like how in the beginning, like when deep learning people started scaling everything up and not caring about proper statistics and just benchmarking, and it somehow works, but now we're trying to understand it, and those methods are kind of problematic a bit if we don't have rigorous statistics to understand it.
I mean, yeah, it's always like as long as things work, you can just put a lot of them. And when it stops working, you need scientists to understand what's.
Like do like last 2 weeks ago or something like that, in Mech Interpreting group, we were looking at a paper that started using language models to interpret language models. The I think it's called activation oracles. Is it called like that, Victor?
Yes.
Or do you know it as well?
Yeah, it's activation oracles. Yeah.
So that makes me kind of think, oh, okay, well, now we are using black box methods to interpret a black box method. That doesn't seem to be like what I'm not sure what to think about that. Like from this statistical perspective, or like this more rigorous perspective, it doesn't seem to be really rigorous. As in, like non-identifiability, for instance, seems to be like very big there. Like, you can train neural network in so many different ways if you're using language model. If you're training language model or not training language model, for instance, or in that case, it was fine tuning. So,
yeah. I mean, I remember that there was a short period of time, thankfully it was pretty short, where people were even trying to do cycle. So they were trying to understand well by giving it like personality tests and things like that. So yeah, as you can imagine, that's not really rigorous.
Yeah, or the IQ tests are very viral,
IQ
for
tests,
example.
yeah, stuff like that.
Yeah, I can imagine that's a big issue.
I
statistically.
mean, for the activation oracle kind of thing, maybe it just kind of works. I think like you could have identifiability there if like the model actually gives different explanations for the from different models and it actually works. But I think the hard part there will be being sure that that's actually the case. I guess it will be interesting to like take some of the activation oracle models and asking the same questions for like a random model or something, uh, or even not a random model, maybe something. It will be a better test of this kind of thing to try things on some real model, but that has been trained on a completely different data set that is about something else. Right? Like you ask, like you take AlphaFold or something, and you use it on the uh, on the on the some language question, because maybe maybe you have some method that seems like it's not giving for response in a completely random model because the completely random model is very different from real models in some way. But maybe you could have some real model that you are pretty sure doesn't have whatever the thing you are looking for is. uh, because maybe it's a narrow model that is trained on some other data set that doesn't have it. And maybe that would be a cool test of some things.
Yeah, for sure. I mean, you don't. I mean, you don't need to always necessarily adopt the full statistical framework. Even like this type of comparative studies would be a great thing to have.
I'm gonna put my conspiracy theorist hat on right now, and I'm gonna throw myself into the wild. I cautiously reject Bernie's statement that to truly identify a causal relationship, you have to do an intervention. Cautiously reject.
Can you elaborate?
Throwing myself into the pool of sharks here. Let's I'm gonna put a very extreme example.
Okay.
And of course, we're very far from this extreme example.
I think I agree with you, but
Hear me out.
Yeah.
If the model is linear, you do not have to perform an intervention, because we can read from the weights directly, through SVD, for example, or through other means. We can calculate the causal relationship directly.
Okay. That makes sense.
So this is an example of a very simple neural network where you do not need an intervention to truly identify a causal relationship. Okay, I understand that we are in a very, very far world from this. Okay.
That makes sense. I think I guess it depends also like on the field. I guess for instance in medicine, like you cannot really calculate it from human states that you can measure. So yeah, it makes sense in if you have such a simple model that you can in a way solve it analytically or like numerically or something like that.
Yeah.
I mean, I think having, but I also have a hot take about this, which is like doing interventions helps, but like in principle, you it's like it's not like interventions are like magically separate from other interventions or something. And if you imagine some like ideal agent looking at data like Solomon of induction or something, it can figure out causality just from observations. So I think this relates more to like people saying that the neural networks won't be able to learn like causality or whatever only from text data, more than in practice people needing interventions to figure out stuff. But yeah.
Yeah, I guess like another thing I came up with just now is just like, okay, I don't know how well this ties into things, but like, let's say you had a model and you in advance you did not know that it was actually like a linear transformation. Okay, you didn't know. Someone gives you like an API to a neural network, and you're like, okay, figure out the causal relationship. Then you're gonna like do some causal thingies. How many like interventions does it take for you to be like with very high confidence that it has some structure such as linearity? I don't actually know how to answer this question.
It ties
But-
very well into things because that's basically the next paper, more or less.
Right. Right.
You have
part of
to. Yeah,
Um,
you can start with a prior with Bayesian prior, uniform Bayesian prior, and then just slowly update with each new evidence.
But yeah, I mean, that's what I'm working on, is essentially. Oh yeah, it's cutting. That's weird. You have your neural network, then you have your explanation, which is going to be a causal model, and the goal is to have a metric that tells you how well aligned they actually are, and the goal is to also have a confidence interval, so like how many interventions it takes you to detect if your explanation is not actually correct.
Hmm. This sounds very useful, definitely. Like what I'm also thinking of that this if you would apply this to Mech Interp, like you know how expensive is it to like for example train a sparse encoder on frontier models. So like if you wanna do all sorts of rigorous statistics like this, the computational budget will go very far as well,
Yeah, for sure.
which is an issue. And it's also interesting how linear probes on random init networks are still so good compared to random chains. I wouldn't. Yeah,
I think it's just crazy the amount of stuff that is just that we just don't realize.
that just I wouldn't expect that. And like so like and then you can measure the statistical significance, I guess, between the linear probes on a random init network and on the actual network, some other one. Yeah. Just
are you
like in
open? Are you
medicine.
open to collaborations, Maxime?
Yeah, I am, absolutely.
Cool. How do I reach out? Does DM you or what?
Yeah, just DM me on Discord. It's probably the easiest.
Excellent. Excellent. Cool. Cool.
Nice.
Rectifies. You haven't said anything. Are you alive? Not to call you out or anything, but I'm calling you out. It might be.
You mean Nika?
No,
rectifies.
the one right below them on my screen anyway. Okay, they don't have to speak up. It's fine.
They can do observation without intervention.
That's nicely meta. Oh yeah.
Any other questions or?
Yeah, you also said that some people are trying to build more interpretable models from scratch, like for instance the sparse transformers from OpenAI, which incorporates the sparse autoencoder ideas.
I am on this train, by the way, of architectures. So.
Yes, same in a way.
Cool.
Yeah, I mean that's the other thing. If you can't interpret existing stuff, just train them to be interpretable.
But seems like at least in the OpenAI architecture, like that we went through like 2 months ago or something here, seems like there's a trade-off between interpretability and capability, at least in terms of deep learning, basically. So that seems to be an issue in terms of like commercial interests and so on, and being more interesting, capability being more interesting to most people than like actual scientific understanding and explanations, basically what Mech Interp is trying to do. So
yeah,
that's
I think that's also it really makes sense that this trade-off exists, because I mean interpretability is essentially like how humans can understand, like, very subjective. And if you want something with better capabilities than you, then probably it's not something that you can explain easily to a human, or if a human could just do that immediately, right?
yeah.
Also, so a problem is when you are doing things like training the models to be more interpretable, is that like I mean, maybe you'd have a method where you have the model and train it to be more interpretable without changing how the model works, but otherwise like what we actually want is to interpret the ones that people use in practice and then we need to be able to interpret those even if they are not trained to be interpreted or whatever. But at the same time, I think we could probably learn very like we could probably learn things. If we had some mod right now, we don't really know how really understand any big model, and if we had some big language model, even if it was worse, or if it was something like the sparse thing that the OpenAI did, that we actually understood, we probably could learn a lot of things that generalize to whatever models people actually use.
I think the really big constraint, like I think the OpenAI approach is wrong. Okay, I'm okay with disagreeing with OpenAI and big labs. I think interpretable architectures is definitely a play. I think their play is wrong, in the sense that they just trade off massive amounts of performance. I think there are ways we should specifically search for things that enhance interpretability that are not extremely harmful to performance.
Maybe we
think
could
they will- I
find a
think-
kind
I
of
think-
trade-off where
I think they
like
will be.
training gets harder, but inference doesn't get worse, or something like that.
Yeah, I think these are all valid approaches. I think I think we've not invested enough like thinking power into exploring. I definitely think that improving interpretability, there's definitely a trade-off. There's no such thing as like a free lunch here. It'll cost something. And the easiest resource, the easiest to articulate resource is performance. But I think there are nice, favorable trade-offs, and we should be searching along this Pareto frontier. That's my take.
I think it would be nice if we have a model it would be nice if we had a method like that, but that also if people find some right now, I would also be okay if someone finds some method that has huge trade-offs but actually works, actually lets you interpret the model very well, because right now we don't even have that, and I feel
Whisper.
like that would already be progress.
Bilinear. Think bilinear. Think about it. I've already calculated how much extra compute it costs. It's 10%. It's not that much. I mean, okay, maybe for $1 billion training run, it's $100 million, sure. But like, as a multiplier of the original compute spent, it's not that high. Anyway, sorry, I'm just whispering. I'm just like.
Nice. Okay.
Anyway.
There's a question in the chat from the guy who didn't talk.
Oh yeah, rectify.
He said like,
I will verbalize it. Quick question. I see
Okay.
the paper advocates largely for a pragmatic approach rather than a realist approach to interpretability. Wanted to ask why. Like just skipping through it, if there's no true explanation to how model works and just approximations, what does it mean for alignment, and how can we trust interpretability based cases if the explanations are pragmatic?
Wow, that's not the simplest question. So we do advocate for a pragmatic approach because no, it's a good question. It's an excellent. Yeah, I'm not even sure how to honestly. I mean, the thing is, I think there are cases where we're gonna have to decide with pragmatic explanations because I don't realistic ones for sure. If I just don't think the current methods are anywhere near advanced enough to do this kind of thing. I mean, think about it. I think one thing is that neural networks are essentially complex systems, right? Just like I don't know, like they are dedicated to having entire fields of complex system features. Just like you have neuroscience that studies the brain, meteorology that studies the weather. And the thing is that neural networks are kind of complex systems that we can actually see because we can measure what's going inside them, like infinite precision. We can measure them in as much as we want, and so it's kind of like the model, like type can use for explanation of scientific systems in general. So yeah, if we find that there's no definition for these, it's like how to explain something like a neural network where we can actually measure every person accuracy and so on. I keep saying that my icon flashes off, so I don't
Yep, you're cutting
think
off a
I'm
bit.
saying-
Nah, yeah, it's okay. I mean, at this point, it's fine. Like,
Okay. Okay.
we're not running it back an hour and 15 minutes. So
Okay. Yeah.
But I think
we
I
will
caught
make
most
do with
of
what we
you
have.
said.
I feel like
Yeah.
during while you were explaining the paper, you were mostly understandable. And like
Okay.
there is a few annoying extra noises, but I can probably fix that later.
Okay. Well, that part works. That's the best.
Regner Twice, I have a
Yeah.
question of like, what? Okay, maybe this is just me like not understanding properly. Like pragmatic versus realist seem similar to me in my head. What is maybe pragmatic? I don't know if pragmatic is like the right word here. Like I don't see. I'm a bit confused.
Hmm.
Unless Maxime got it.
Yeah. I mean, I think by realist it was more like theoretical or like actual guarantees of understanding. I think that's the part that I meant versus pragmatic. Yeah, I think pragmatic and realist are the same thing. It's just probably the person meant. Yeah, more like theoretical by realist is what I assumed at least.
Okay. I more understood it as like in terms of like predictive power, as in like a realist would be like ultimate predictive power in a way, and pragmatic is fine with error bars, etc. But yeah, I'm not sure a realist is realistic. So, or maybe you wanna define it, Rectifies in the chat. Yeah, he's trying to define it now.
Yeah.
Like,
Realist would be like network has an algorithm and our job is to find it.
So basically, absolute certainty. That's what I mean.
Okay.
hmm.
Yeah, I don't necessarily know that realist is the right word for that.
That is certainly a take. That is certainly a position held by some people. I don't think it is held by everyone. Maybe
feel
held by
like-
Anthropic.
Like I feel like you can say that this would be the ground truth. Like if you exactly one-to-one matched exactly the dynamics in a way. So like, and but in practice, everything we have so far is like, as far as I understand, different approximations for different parts of the network, like different behaviors from different angles with all those issues that you are showing in this paper, basically. Yeah.
I mean, I guess also we have to consider that even if in theory these problems would have perfect solutions, networks don't actually implement perfect solutions because they go by local minima, so they might actually legitimately not be implementing a perfect algorithmic solution even if one exists in theory.
That's true.
Like the
Okay. Yeah. I think pragmatic is there's no single true algorithm. There's only explanations that work better or worse purposes. I mean, I think there's space in the field to be taking both approaches.
Yeah, absolutely.
Like, so I'm just happy that people are actually doing both approaches, right? The realist, like I think OpenAI's work is quite similar to network has an algorithm and our job is to find it, except with an asterisk that they are conditioning the network to have this property. And then like pragmatic, I think in a sense your description of pragmatic is the more realistic view of in terms of like how the field will evolve into. But anyway, yeah, like I'm team pragmatic. I like that, but I think it's good that we have both.
I think it also really depends on why you are trying to explain your system in the first place. If you're just trying to do like predictive stuff, then like yeah, you're probably fine with pragmatic approach. But I would also argue that science in general is kind of trying to understand systems as much as we can, like really get to the heart of it. And I think for that you would need probably more of what you call the realist approach. But I don't know if it's actually doable in practice. That's the main thing.
Medicine seems to be very pragmatic.
Yeah, yeah.
Yeah, especially medicine targeting the brain. But that's maybe because I've explored that one the most, and I don't see the issues in all the other subfields. Yeah. Like, it feels to me kinda like that even like the only like quote unquote realist thing would be exactly the network on itself, like as it's trained with all its weights in all its black box complexity,
Mm,
and like maybe not, but
I
like
feel like at that point,
there is some
you,
isomorphism maybe.
or you might as well say that the true realist thing is a complete description of all of the atoms in their computer or whatever, and like you kind of like remove the concept of explaining something, which in the end it is about having some high level abstraction that is kind of works like that most explains most of the things, even if you have some noise or whatever that you don't care about. Right? Like you can explain a human body by either saying it has organs and that do specific things and their cells or whatever, or you can explain the human body as a giant pile of atoms that follow the laws of physics. And
Both are correct. Yeah.
in some sense the giant pile of atoms is more correct than this. In that there are other things that you are not going to capture on the other thing, but that's not like when we talk about understanding something, we're already thinking about higher levels of abstraction and ignoring some detail and things like that.
Yeah.
Well, the one detail is also here when we're doing Mech Interp, we're not trying to explain usually the entire network, but more like the behavior of the network on one specific task. So I don't think it's not necessarily an insane take to think that surely we can do better than having the full computation. Surely there's all kinds of parts that are inactive, even with polysemanticity and redundancy and so on. Like probably there is some kind of compressed explanation that we can find.
Yeah. Like you can find a compressed explanation for the entire network. It's like in the same way you can I think you can like medicine can understand the human body without having without having a complete list of all of the atoms or whatever. You can find compressed explanations for all the different parts of the thing, and
We
get
don't need standard model.
predictions in all kinds of situations. And that feels like a separate thing from another meaning of like thinking more about pragmatic of more the thing that people do in medicine versus biology, where in medicine people usually yeah, yeah. I think that your thing does the question does edges into philosophy, but yeah, I think that this seems like a separate thing here where you can have different, not be trying to explain something where you just care about some local property, like will this medicine work, and then you might just be black box looking at it and trying different substances and seeing what happens. And yeah, it feels like there is like this question of uh, what does it mean to explain something in separate for like the more there are more pragmatic methods and less pragmatic methods that are more about understanding. But like, so
Hmm.
what is the okay? So what I'm trying to say is, yeah, I'm not sure what I'm trying to say. I feel like I kind of getting lost in the philosophy right now. Sorry.
Makes me think about like, have you seen Maxime? Have you seen the Neil's pragmatic interp paper or
Yeah,
blog post?
I have.
Right, which one?
I see some related patterns
Which
with
which
your
blog post
work.
are you talking about?
Neil posted that he's
Oh,
quote unquote
yeah.
moving from trying to
Yeah.
find the algorithm to figure out the methods that work for alignment. So this way, like being pragmatic, basically. So
Yeah.
like methods that work the best, not that explain the most or something like that. Like to summarize it very high level and probably straw manning or something.
Yeah, I feel like Niels thing is more about he's trying to, like, more about a changing approach of how he he and this my team periodize research more than anything. And it's not that, and he's also giving up on trying to fully reverse engineer networks. But I think if he thought it would be likely to be doable to fully reverse engineer networks, I think his pragmatic approach will recommend doing that. So it's not like I think these are separate things. Kind of. It's kind of complicated. I asked him about it on the channel, and he said some interesting things. Like it's on the reading group channel of some a while ago when we read his post on the reading group. But yeah, where it's more that he used to take fully reverse engineering the neural network as the main objective, and now he's trying to has his main objective is trying to do whatever is useful for helping with alignment with interpretability.
Yeah, okay, that makes sense actually.
Yeah, but like if he thought that fully reverse engineer the neural network was going to be easy and useful for interpretability, he will do that. It's just that he's not focusing on that as his current objective, where he thinks of all the methods if they are good in terms of do they help for that or not, and he's more fine with kind of hacking, like the kind of methods that just work for now and just solve
Yeah.
some problem, like tell if the model is lying or whatever, even if they don't help with reverse engineering the model, understanding it better.
That's true.
I gotta hop out, but before I leave, I would like to, if anyone has ideas for the server, DM me those ideas. I'm gonna try, instead of talking on the server, DM me directly. And also, if they want to talk to me about any research at all, DM me as well. This extends to the people strictly in this voice call to keep it tractable.
There will also be people on the watching this on the YouTube channel, maybe, though.
Oh yeah, extends to them as well, but no one else. I mean, who else is gonna hear it? But anyway, I'm gonna hop out.
Now the video somehow become super viral and you start getting
Yeah. Anyway, cheers.
I don't think
Cheers.
so, but yeah.
This is a good talk. Thanks for giving it. I'll try to.
Bye.
Thanks for the
Okay,
question.
so yeah.
Bye-bye.
Yeah, it's true. This paper is more like I kind of see it as kind of like meta interpretability, like
Yeah.
trying to interpret how the different interpretive methods work and don't work, and how to make them better, basically as a result, which is good. Which is different from Neil's reprioritization. So this is more like trying to actually make the methods work better and actually reverse engineer better, and so on. Yeah, and like. And we should meta interpretability. And yeah, that would be meta. I guess this is also a form of meta analysis, since you kind of review the different papers there.
Yeah,
Yeah.
it is in a way.
So we need more of these, I think. But this is good. Like I it's interesting how in science, like, the more you go into the methods, the more holes you see in them and so on. Oh well. Makes you feel less and less confident about the results as a result.
Yeah, but I mean, on the other hand, if you think about it, we are in a much better position than neuroscientists because neuroscientists can't get the entire activations of every neuron. They get only population averages and things like that, and they have to go from there. So we should be better off in Mech Interp.
Yeah, and they
Yes.
also can't remove half of a patient's brain and see if a behavior.
That reminds me of like I saw in a conference I was with David Bao, and he was trying to convince one of his students when he was doing neuroscience to come work in Mech Interp, with saying basically that you don't have to do like the experiments are much cheaper, and you don't have to spend months to like remove parts of a mouse brain or whatever.
Uh-huh. Yeah, but if you wanna do it on frontier models, then you need very big pockets of money.
Yeah, that's true.
That's, I
I
guess,
mean,
one
depends on what,
disadvantage.
but yeah.
Yeah, that's
But I
true.
guess even
Depends.
for frontier models, even if the open source best models, even running them is expensive. So
Yeah.
unless you want to run them very very slowly, using swap or something, but yeah. Uh,
Huh. I wonder if there is something like if you could like train sparse models on different sizes of models and see some scaling laws in interpretability or something like that.
People have a read all that kind of thing. But like, I guess it's kind of hard, like how you measure. I think, I mean, there's a bunch of papers. I think we've been saying on the reading group that have different. I don't know if scaling laws, but yeah, that show for different models of different sizes things, or like show some relationship with the sparsity of the sparse encoder or whatever, with some other measure of how well Wood is interpreting. But I don't know.
Hmm. Makes me wonder if the bigger models also like have more paths to solve some concrete tasks. So like you could identify more circuits in a way for the same task.
That feels more like this feels like the kind of thing where you can probably figure something out from existing papers that have already looked. Like I feel that there's a bunch of papers that were like looking into things related to that like we're not mainly trying to figure the thing you are asking out, but where they were trying on different models, and some of them are bigger and some of them are smaller, and you can probably figure it out by like doing literature search or whatever, and asking Claude or something for to look for papers on that, and yeah, looking at what they found. Or even there's probably also papers that look at that kind of thing on the small models, and other papers that look at the same kind of thing on bigger models, and you can figure maybe that out. I don't know.
Hmm. Yeah. So if you could have multiple circuits in a model, and you could have non-identifiability in terms of using different methods to identify them and finding. No,
I
yeah, having multiple circuits for the same circuit basically, and there being multiple circuits in the model as well, and in the interpreted method, in the method that interprets it. Oh well, get it. Fancy so hard.
Something I feel it would be cool to test of all kind of methods. It would be really nice if we actually like. That's why I like the OpenAI thing. I think that's like if I don't know, Wook managed to find some bilinear thing or something that just works, that would be nice. But even if we have a method that makes models that are like trained to be more interpreted or whatever, and they are much worse, but we actually understand them, that will be really good, because then we could test things like identifiability by having a model where we know what the answer is and testing methods against it.
Yeah.
But we also don't have a model where not only like we don't even have a model that where we have some vague guess of how it works. We don't. We will need a model where we are pretty sure we know what it works. That seems even harder. And right now we don't even have like some model where we have a full circuit thing that explains the model that we are not sure it's true, but it's at least some full explanation that like explains most of the answers of the model, whatever.
There's the Mech Interp benchmark. Actually, that's kind of how I started my PhD. I wanted to make a benchmark to try to have like provably interpretable networks, and then we could try the methods on them. And that's what they did pretty much in the Mech Interp benchmark. They used interchange intervention training to do this like causality-based training, and then they submitted it as a benchmark, and people can just try and recover the original circuit. But it's just for circuit finding, so it's only one Mech Interp method.
Yeah, I think there is some things you can do with synthetic circuits that you made, and then you know what the ground truth is. But I worry that kind of thing is worse in that they don't. Like the real models are going to be pretty different in some ways. Like I don't know, you could, for example, you could train with like you could code. There is a thing called Tracer from Google. I think it's from Demand, where you can write code and compile it to a transformer. But I don't think I expect that looks like very different from actually trained neural networks in ways that's probably testing your methods on that probably doesn't.
Yeah, I mean the weights are basically binary. Like of course it's very different, but at the same time, I don't know if our methods don't even work on super simple things, even if they look very different. Like I think it's unlikely that.
Oh yeah, that probably is. It probably should be tested like kind of similar to the random model thing. It will be nice to see what happens if you want to try what happens if you have those models tested. I was thinking more, even if it does work, that still doesn't mean it's going to work on a real network. But yeah, maybe the other way around. Your method should probably also work on the binary thing too, unless I don't know your method does exploit some feature of real networks that the binary thing, like the tracer thing, doesn't have. Like maybe turns out something like this is actually something I don't think is actually true, but maybe everything is the linear representation hypothesis is just true, and so and you can just use some kind of sparse encoder to interpret the neural networks, and some tracer kind of thing wouldn't work. I don't think that's actually the case for that example, but something like that.
Like if you had a method that really needs your model to be noisy and messy and having Poisson identicity and multiple directions and stuff, I mean, if you've managed to find something like that, sure.
Like I kind of the original modular edition transfer paper from the Groker paper. That it makes me wonder how holes in this paper.
I at least not hearing you very well right now. Like it's not very.
Okay, maybe now.
Oh, now it works. Yeah.
Better.
Yeah. So the original Neil Nanda Groking paper with modular addition algorithm reverse engineered being the trigonometric algorithm. That makes me wonder if how many holes are in this paper. Like, how is it? Is it also non-identifiable, for example, or like if you did this method on a random init network, what results would you get, etc., etc. Basically, do this paper on this Groking paper, like, which seems to be like, as far as I understand, the most. It feels the closest to the ground truth of what the transformer is doing, but maybe we're actually deluding ourselves.
I did. Okay, so I have been looking recently again to my thing with the auto-contest learning stuff on a modular multiplication model, and I don't know the rest, but okay, some things on the original Grokking model does seem like pretty clear, does work like that way. And also seeing the same things on a different model that's trained on modular multiplication instead. So I don't know. I will want. I know I want to try the experiments I was running on the other day, but like on a random network. But I think at least the Fourier decomposition stuff, it's unlikely you find like so clear results as in the Grokking paper with a random network. But yeah, let's prepare the other stuff.
Yeah.
Also, I don't know so in one hand they do the thing where they replace the model, the parts of the model with their math for how it works, and that doesn't hurt the performance very much. But I don't know. I will have to check like the details of that and how much it works to be sure that it actually makes sense. But yeah. But going to that, I will see like people working more on that kind of Grokking model, like with the modular addition model, and like actually getting pretty confident you know how it works, and maybe that could be a good test of some methods. See if they recover the same, Grokking. It's the same Grokking. No, I mean the same modular addition structure. For that, it will be nice to have more examples than the modular addition thing. At the same time, I do worry that this kind of thing, this kind of toy model, it's also pretty different from bigger models, so it might not generalize that much. But yeah, could be. It should at least work. Like your methods should also work even for those small models. Also, on the related to that, I do expect I wonder if the Grokking model also has a nice. I was thinking about that the other day. Also has a nice geometric explanation, like with the other, like in the other.
The spirals.
Yeah, I actually was looking for that the other day, the modular multiplication model, but it's instead it doesn't have a nice spiral though. Like it instead has like a bunch of clustering where it. I think it is also the same on the modular addition model though, where it's more that has a bunch of directions on the embedding space, where each direction, like each number is clustering, like are clustering some direction, and some direction means that the number is some module or something, and it just finds the correct number with that. Like it has a bunch of this number mod 5 is 5 or whatever. This number mod 18 is whatever, and it just combines those to differentiate all the numbers. It doesn't have a nice continuous curve, but
that's this weird composition, maybe.
yeah, so it does look
Okay.
like a cool structure thing, but it's not a cool. I think it's. I mean, it does end up being like a nice Fourier like decomposition thing. I feel there has to be some way of plotting it where it looks like a circle. But yeah, I need to think more about that. I was just mostly asking the cloth for output 4.5 to do things to see how well it did at the kind of.
Nice.
Yeah, but I hadn't done much. Like I was working on something else in that project. Now I was not looking at the modular multiplication anymore. I was looking at the real language model now, but I went back for the modular multiplication thing for a bit to test. To see if Claude will get to the same conclusions I got for like just letting it run experiments.
I wonder if you would train it in some different way, if you would get a more clear geometrical structure as a result. But
yeah, I don't know. I mean, you do actually. Okay, so big language models like GPT-2 do have a nicer geometric structure because they have there's one of the papers, the language models use trigonometry to do addition, and so they do have an helix for that.
yes.
But I think the thing on the Gorkin paper is not the same, but maybe I'm not completely sure. I feel like I thought they were the same, but then I was confused yesterday, and I might still just be confused. I'm not seeing how it is a thing. But it's not the case that if you just plot the PCA, like when you plot the PCA on the other Spirals paper from Anthropic, the more recent one, it doesn't look like that if you plot the PCA. It looks like a bunch of it looks like some of the numbers are clustered, and if you look at that, it turns out the clustering depends on the mode of the being mod 5 or something. But maybe you take the Fourier transform or something, and then it looks more like a circle or something. I'm not sure. I will look into that and tell you later if I figure that out.
Okay.
Anyway,
I
feel like
wonder if
we
that's
were
because
kind
of more
getting
training data.
away from the original topic and the paper, and maybe we could, or like, I don't know, if we could also end it here if people don't have a lot more to talk about this paper.
Yeah, I will have to go shortly, actually.
Yeah. Does anyone else has any questions then before Maxime has to go?
Doesn't seem like it.
You know,
Maybe one.
okay. Yeah, the certifier says he doesn't have questions. Okay.
Thank you everyone for the questions. The discussion was super interesting. So thank you a lot for that.
Yeah.
Thanks for the presentation, Maxime.
Yeah, thanks for coming. If you want to you make another paper and you want to come talk here, just say it on the reading group and I'll probably
The next one is probably gonna be in a while, but sure.
Yeah, okay. Also, a last thing I want to say is, yeah, now I was thinking of this, and maybe I kind of want to try taking a random model and asking Claude to try to figure out what it does to see if it comes up with some random fake explanation.
Yeah, if you do that, I'm curious to see the results actually.
Yeah. I don't have that much usage for Cloud because I'm only playing the $20 thing, so it's going to be a while. But yeah, yeah. I also want to see that for the activation oracles. Like if you take a random model, does it actually answer the question? Or if you ask a question of the activation oracle that it can't, like it's impossible for it to answer.
Like, what makes me think they technically tested it on different models, I think, and they found like a loss in performance. So I would assume completely random model would be big loss in performance. But I wouldn't be surprised anymore after this paper.
Yeah, like it is probably a big loss in performance, but my question is, does it does the model say it doesn't know how to explain it, or does it hallucinate the explanations? Like, how does it fail? It probably you can already see on the other model's case, like how does it fail? Like, does it like make up things? Maybe it hallucinates on the other models, but on the completely random one, it says it either goes crazy or just says it doesn't know. I kind of expect it doesn't. It kind of just mixes things up. Just that's a problem because like when you are testing, you do know. For the relativity of course, they do know the ground truth, but the interesting thing is finding out like cool. Yeah, like I guess from the back door, I wonder if they tried asking it for I don't remember if they tried that in the paper. They tried asking testing it on a model that to look for a backdoor in a model that doesn't actually have a backdoor. But yeah. Anyway, yeah, I guess we can leave it here. If nobody else has anything to say.
Okay.
Yeah. I'll stop the recording then. Where was it? Here.
I'm still